let's take a look at inverse functions. And first thing you want to look at is one-to-one functions. Our definition of one-to-one function says, for every x, there is only one y, and for every y, there is only one x. That's a very hard definition to use unless you're dealing with points. So we're going to look at an easier definition. Our easier definition says if you have one of the following, it is not a one-to-one function. Now it might be a function, but it's not a one-to-one function. You got x to an even power. If you got y to an even power, if you got the absolute value of x, or if you got the absolute value of y of some sort, if you got the plus or minus symbol, then it's not a one-to-one function. If you got x is equal to a number, or y is equal to a number, like x is equal to 3 or y is equal to 5, then it's not a one-to-one function. Unless there is a condition put on x. And what I mean by that is you have y is equal to x squared and that right there, since it's got an even power on the x, then it would not be a one-to-one function. But if they put a condition, they say where x is greater than 0. By putting that condition on there, college algebra books, you typically are putting that condition to make it one-to-one. Now we got a horizontal line test that says, remember the vertical line test was if any vertical line intersects your graph at 2 or more places, not a function. The horizontal line test says if any horizontal line intersects the graph at 2 or more places, it is not one-to-one. It might still be a function, but it's not a one-to-one. So the horizontal line test just determines the one-to-one portion. Example of that. There it is. If I have this graph right here. Well, the question is whether I can draw a horizontal line that intersects at 2 or more places. Well, if I draw one here, I see it intersects at 2 or more places. So this is not one-to-one. So that's an example of one that's not one-to-one. Now, on the other hand, if I have a problem that looks like this. Well, if I draw a horizontal line here, it intersects one place, draw one here, one place, draw one here, one place. No matter where I draw a horizontal line, the most it'll ever intersect is one place. That means, by the horizontal line test, that this is one-to-one. Clean that off. Okay. Why do we care? What did one-to-one tell us? Well, mainly what we're going to use in this section is if it is one-to-one, then it has an inverse. If it is not one-to-one, then no inverse. So if you got a problem that's giving you a graph or just a function, and they're asking you if it has an inverse, they're really asking you first determine if it's one-to-one, and then from the one-to-one you can then tell whether it has an inverse. Okay, now that's the first. Identify one-to-one functions and why we want to do it. The next topic, although it isn't on the list there, is what is an inverse? And we're going to look at this graphically. Inverse functions are symmetric to the line y is equal to x. What does that mean? Right here, is the line y is equal to x. Now if my function looks like this, and that's labeled as f, or f of x, to say it's symmetric to this line means you can take this part of the graph, flip it across that line y is equal to x, and as close as I'm going to get, it'll look like that. So you're flipping it across, you're reflecting it across this line, and that's going to give you your inverse. So that's what inverses mean graphically. Let me clear that off. And let's talk about what they mean algebraically. Inverses of functions algebraically. F and G are one-to-one functions and are inverses if the following is true. I'll make this a little bit bigger after I add it in. I'm out of town, so I don't got my regular equipment at home, so you have to forgive the quality of this video and how slow this is. And that is extremely slow. Let me try that again. Close that. Insert object. There it goes. Microsoft equation. And I got the composition of f and g is equal to x, and the composition of g and f is equal to x. That's what it means from an algebra standpoint. Well, let's take a look at an example. If I have f of x is equal to 3x, let's try it again, 3x plus 2, and g of x is equal to 1/3 x minus 2/3. And let's say the question is whether the inverses of each other or not. First thing I'll do is find the composition of f and g, which is f of g. So we're going to take our f of x, which is 3x plus 2, and where our x is, we'll put in a set of parentheses. And I need to have my color back, I think. Maybe. There it goes. There we go. this will work better. Now, remember with evaluating, whatever's inside the parentheses here is automatically what goes in here. So we're going to put G in there. But G is equal to switch those. There we go. G is equal to 1/3 x minus 2/3. Now if I multiply this through, 3 times 1/3 gives us 3/3 or 1, so that gives us 1x or x. 3 times negative 2/3 gives us negative 2 plus 2. Negative 2 plus 2 cancels and we got x. So that's our first item. It has to give you x. For our second item, we want to find the composition of G and F, which is G of F. So we're going to go to our G of X, which is 1/3 x minus 2/3, and I'll replace the x with a set of parentheses. Now this is evaluating, so whatever's inside the parentheses right here is automatically what you're going to put in right here. So we'll put F in there. But F is equal to 3x plus 2. So we'll replace the F with 3x plus 2. Now if I multiply the 1/3 through, 1/3 times 3x gives us x. 1/3 times 2 gives us 2/3 minus 2/3. 2/3 minus 2/3 cancels and we got x, and so that gives us x. If the composition going both ways gives you x, then the answer is yes, these are inverses of each other. That's what it means to be inverses of each other algebraically. Now let me clear this off. A little bit slow. Quite slow, actually. Okay. Now that's determine whether two functions are inverse. And our third item we're going to find is find the inverse function. We won't look at all the items in all of these because we won't have time, so I'll kind of skip around a little bit. Now to find the inverse. Specifically inverse of a function. Step 1, replace f of x with y. Now this is assuming that that it's 1-to-1. If it's not 1-to-1, it doesn't have an inverse. Okay, step 2. Interchange x and y. Swap them. Step 3, solve for y. Step 4, replace y with our inverse notation. And step 5, if necessary, use the graph to help figure out how to make the inverse function 1-to-1. Now specifically when you say that, that means you end up with one of those items we said you cannot have. You can't have x to an even power, y to an even power, absolute value of x, absolute value of y, or plus or minus. So let's take a look at finding the inverse. We got f of x is equal to 1/3 x minus 4. Step 1. Replace f of x with y. So you got y is equal to 1/3 x minus 4. Step 2, interchange x and y. Swap them. So we got x is equal to 1/3 y minus 4. Step 3, solve for y. Well, the first thing we want to do here is we want to multiply everything by 3 to get rid of the fraction. So we'll take 3 times x. We'll take 3 times 1/3 y minus 3 times 4. So that gives us 3x. Those 3's cancel. I get 1y or y minus 3 times 4 is 12. Now we're trying to solve for y, so I'm going to take the negative 12 over the left side. So we've got 3x plus 12 is equal to y. Step 4, replace y with our inverse notation. So we got the inverse of f of x, or the inverse of f of x is equal to 3x plus 12. And that's our answer. It's already 1-to-1, doesn't have a x to an even power, y to an even power, and so forth. Let me clear that off. And then we'll look at a little bit harder one. Okay. Let's take a look at f of x is equal to the cube root of, I don't know, x plus 2, I guess. Step 1. Replace f of x with y. So we got y is equal to the cube root of x plus 2. Step 2. Wonder if I got this full size, or how I could even tell. %. Let me zoom out a little bit. There. I think that'll work better. Okay, so step 2, interchange x and y. So we got x is equal to the cube root of y plus 2. Now step 3 is to solve for y. So I'm going to take both sides of the third power. And that gives us x to the third. And over here the cube root and the third power cancel each other. And that gives us y plus 2. Take the 2 over the other side. We've got negative 2 plus x to the third equals y. Step 4, replace our y with our inverse notation. So we've got the inverse of f of x is equal to, and I'll flip those around actually, x to the third minus 2. And that would be our answer. Okay, let me clear that off. I'll grab a drink while it's clearing off. Okay, there we go. Now, section 4.2, exponential functions. Let's take a look at graphing those first. An example. We got y is equal to 2 to the x power. An exponential function means you got a variable in the exponent. And I want to graph this. I'll go to my calculator, press my y equals, press my clear. I'll do a 2 caret x and then graph. Now these graphs always look like they stop. They never stop. So this actually goes for, oops, went down a little bit too far. Yeah, if I get it to draw finally. It keeps going forever this way, getting really close to the x-axis, but never touching it, never crossing it. It skims it. That's actually an asymptote. And our graph looks like this. If we have y is equal to 3 to the x plus 1 and minus 2. If you got one of the older T83s, T84s, you have to be careful about putting this in. The trick to it is, whenever you have more than a single number, a single variable in your exponent, you have to put parentheses around that part. So when we plug this in, we need to put parentheses around the x plus 1. Okay, so I'm going to go to my y equals, clear, and then I'll do 3 caret, beginning parentheses, x plus 1, closing parentheses. Now if you got one of the newer T84s, you don't need the parentheses around the x plus 1, but you do need to do a right arrow key to get out of exponent mode. What I mean by exponent mode is if you see a caret like this, you got one of the older T84 operating systems. I don't care if you just bought it yesterday, it's one of the older ones. It would look like an actual exponent if you had one of the newer ones. And again, to get it out of the exponent, you press your right arrow key. And then minus 2. And then graph. And that would be our answer. I won't sketch it down, but now you might have one involving e. Like this, y is equal to e to the x plus 3. Now e is a number like pi. It's 2.7 and a bunch of decimal places. How you get e on your calculator is you're going to do second and then the ln button. Now the ln button is the natural log. So if I go to graph this, I press my y equals, press my clear, I do second ln, it puts a e, puts a caret, puts a beginning parentheses for me. Then I'll put in x plus 3, and then I'll press graph. And that would be our graph. Remembering it never stops, it keeps going forever, skimming the x-axis as it goes that way. They all follow the same pattern. Now that was graphing it. Now evaluating the exponential function base e, we've seen how to do that. Specifically how to get to e. Now if you were asked to evaluate, as soon as this comes up here, if you got f of x is equal to e to the x minus 4, and it asks you to find f of 3. Well, this is just evaluating the function. You go through, and everywhere you have an x, you'd put in whatever's inside the parentheses here. So we'd have e to the 3 minus 4 power. Now to plug this in, you want to be out of graph mode, so you do a second mode, exit out, do second ln, it puts the e caret beginning parentheses, and then 3 minus 4 is a negative 1. You could put 3 minus 4 if you wanted, but it's negative 1, and then press enter. And I'll take it 3 decimal places, I guess. And we get 0.368. And that'd be how you evaluate a exponential function. Let me clear that off. Now we have compound interest formulas that deal with exponential functions. Now for our compound interest, You got two types. The first one does not say continuous. So it does not say continuous. It might say compounded quarterly or compounded monthly. And it's A is equal to P times 1 plus R over N to the NT power. And then you have your second type that does say continuous. And it's our PERT formula. We got A is equal to PE to the RT. Now you might have an example that says your principal is 1,000. Principal is how much you're putting into your account. The rate is 2%, and you want this in decimal form, so if they tell you 2%, you put in 0.02. You're going to leave it for 5 years, compounded monthly. Now, N is the number of times compounded per year. If it says compounded monthly, that means N is 12. So then, we would plug these values in. P is 1,000. We got 1 plus R, which is 0.02, divided by N, which is 12, raised to the NT power. So I got 12 times 5. It's best to do a little bit of math before you plug it in your calculator. You got 1,000 times 1 plus 0.02 over 12, and 12 times 5 is 60. So now we'll plug that in. So you get 1,000, beginning parentheses, 1 plus 0.02 divided by 12, close parentheses I meant, then caret 60, and then enter. So we got 1,105 and 8 cents. And that would be our answer. Now on the other hand, if they told you in a different problem your principal was 2,000 and your rate is 3%, so R is 0.03, and you leave it in there for 10 years, so T is 10. T as always has to be in years. And it says compounded continuously, so it uses the word continuous. Then you would use this PERT formula. So plug 2,000 in for P, E to the R, R is 0.03. Now put a little X here for times, T, which was 10. Now you have to be careful on inputting these into your calculator. So if we come over here, I do 2,000, E, you do second ln, and you do not want to put any extra parentheses in here. That's why I put the little X there. And I'll have 0.03 times, what was it, 10? Times 10. And then that tells me we got 2,699, and how many cents? 72 cents. Now that shows you two examples of figuring compound interest. And that's actually encompasses both of these. Use exponential functions, compute compound interest, and use exponential functions in applications. So let me clear this off. And we'll look at the next section. Guess I can grab a drink. Drink for me is Diet Dr. Pepper. Okay, there we go. Now, section 4.3, log functions. First thing we'll look at is converting between log and exponential forms. Okay. Now our log form looks like this. We got log base b of q is equal to p. Now all of these probably have names, but the only one that's really important is the b. That's referred to as our base. It's usually a little number that's smaller that's set down. Now if we have it in log form, we can rewrite it in exponential form, and that's b to the p is equal to q. Now going the other direction, if you have it in exponential form, you can rewrite it in log form. Okay, so let's look at an example. I got log base 3 of x is equal to 7. And instructions, write it in exponential form. Well, you first have to identify all your different pieces. Again, the number that follows your log that's set down is your b, so the 3 is our b. And then what follows that is your q, so the x is our q. And then the other side of the equals is our p. And our exponential form is b to the p, maybe, if it wants to write. There we go. B to the p is equal to q. I was hoping at least to get an hour of this session. With this older computer, which has the proper software so I can write on a tablet, it's got less memory, so I don't think it'll last more than an hour. Okay, so now we'll plug in our b, which we said was 3, to the p, which is 7, is equal to q, which is x. And this is exponential form. Boy, that's just not working well. There we go. Now if you have something in the exponential form, if you have 5 squared is equal to 25, and they want you to put it back into log form. Well, if I match this against my exponential form, my power, my exponent is my p. So the 2 is going to be my p. What's immediately left of that is my b, so the 5 will be my b, and the other side will be my q, so that'll be my q. And our log form is log base b of q is equal to p. So I'm going to plug in what I identified. The b we said was 5. The q we said was 25, and the p we said was 2. So that's going to be our log form. Now we have some special bases. So let me clear this off and we'll talk about those. Okay. So special bases. One of them is if you just have log, there is no base. There's no number that's smaller that's set down. This by default is the base is equal to 10. This is our common log. If you have ln, that's natural log. your base is e. Now it looks completely different. It doesn't say log anymore. It says ln. It still has all the same properties as the other one. Just our base is implied. Now, if you're wondering why is it natural log instead of NL, we have LN. This is French. It log natural. So, if I have something of this form, let's say we got y is equal to log of 7, and we're wanting to write it in exponential form. Well, our base would be right here, and since there is no number and it says log, our base is 10. Then whatever follows this will be our q, and the other side is our p. And our exponential form says b to the p is equal to q. So we'll plug in what we found. B we said was 10 to the p power, which was y, equals q, which is 7. Now, if I have something in exponential form, I have this. E to the 7 is equal to x plus 1. Well, first we need to identify our b, p, and q. Whatever your power is, that's your p. Whatever is to the left of it is your b, and then the other side of the equals is your q. And our log form says we got log base b of q is equal to p. So b we said was e, q we said was x plus 1, equals p, which is 7. Now whenever you have a base of e, you automatically rewrite it as natural log. So this is natural log of x plus 1 is equal to 7. And that would be our answer. Okay, let me clear that off. And then we'll look at the next topic. I've had this older computer here for a long time. Still works. I got a newer laptop, but I haven't got the software working on it. So I have the power, but I don't have the software. Okay. Now evaluate log expressions. So let's talk about that. And also along with that is apply basic properties of logarithms. If I'm trying to evaluate log base 2 of 8 without a calculator, I'm going to do one problem and then I'm going to talk about the property. Property will make it look kind of complex, but it's a fairly simple idea. What we do is if we got numbers, what we try to do is we try to rewrite this number here as the base to a power. For example, I can rewrite 8 as 2 to the third. Now, if you can get these numbers matching, then the log and those two numbers are going to cancel. And the exponent drops out of the exponent, and our answer is 3. Now, the property for that says we got log base b of b to the p. Let's try it again. Log base b of b to the p is going to equal to p. Sometimes they're not so easy. Like if I got log base 5 of 1 over 25. Well, to begin with, I can rewrite 25 as 5 squared. That's giving me a step closer. But in this example, the 5 squared is trapped down in the denominator. But that's okay. We have a property that says we can move it up on top. And when you move anything opposite of where it's at in the fraction, the sign of the exponent changes. So the 5 to the positive 2 becomes 5 to the negative 2. Now once I do that, I notice that these numbers match. So log and those 5s is going to cancel. The negative 2 drops out of the exponent, and our answer is negative 2. Now there's another property. I'm going to work the problem first, and I'll talk about it. But let's take a look at this problem. If you notice something, this 5 here matches the base of this. This says 5 to the power of log base 5 of x plus 1. When these two numbers match, then those two numbers in the log are again going to cancel away. The x plus 1 will drop out of the exponent, and that's our answer. Now the property on that. Property says we got b to the power of log base b of q is going to equal to q. Pretty simple idea on these two problems. Not always simple to get it in the correct form, unfortunately. So let me clear this off. Okay, there we go. Now that's evaluating and applying basic properties logs. Now to graph log functions. Let's take a look at that. Some of them pretty easy, some not so easy. If we have f of x is equal to log of x minus 1. Well, we just come over to our calculator. This is base 10 because there's no number here. That's a common log. So if I come over here, press y equals clear, log of x minus 1. And you can put a closing parentheses if you want, and then press graph. This is almost our graph. Calculator never gives you the correct graph. Well, there it goes. They never just stop. It keeps going forever this way. It's a flaw with the graphing on a calculator. It always looks like it just stops on the screen, but it never stops in real life. Your graph keeps on going forever. Let's take a look at a natural log. Let's say we got x minus 3. Again, pretty straightforward. I go to my y equals, go to my clear, natural log of x minus 3, and then I press graph. Again, they never just stop like this is looking like. So this is going to go down forever like this. So that'd be what your graph looks like. Okay, pretty straightforward. Now let's take a look at another graph. Straightforward if you got TA3, TA4. Okay, so let's say I got log base 2 of x minus 1. We got two buttons on our calculator. We got a log button, which is base 10. That's our common log. We got our ln button, which is base e. That's our natural log. We do not have a button for base 2 because you can put any number there. So I'd have to have an infinite number of buttons in order to handle that. What we're going to do is we're going to rewrite this using the change of base. And this is going to become log x minus 1 over log 2. Now how that works is whatever follows your log always goes up on top. Whatever your base is always goes on the bottom. Now you might be looking to say, well, that's more complex. What have you accomplished? We have a log button, base 10, so this I can actually plug in my calculator. Change of base says you can actually rewrite it with any base. I could rewrite this as natural log of x minus 1 over natural log of 2. Again, same idea. Whatever follows your log goes on top. Whatever your base is goes on the bottom. Why is this important? Well, we have an ln button, so I could put that in. Doesn't matter which one you use. Both of them give you the same graph. The change of base says you can actually change it to any base, but those are the two that makes most sense for college algebra. So let's go ahead and graph the top one. So I'm going to press my y equals, press my clear. I got log of x minus 1, closing parentheses, divided by log of 2. And I can put a closing parentheses at the very end if I want. I don't have to. And then I'll press graph. Now again, these graphs never just end. This keeps going down forever. It's a flaw with the calculator. But that would be our graph. Okay. I'm not going to show applications because I'm going to have minimal time to show all this anyway. Now this says apply the product, quotient, and power properties of logs, and that kind of goes hand in hand with the next two. And I've already showed the change of base here, so I won't show it again. Okay. So log properties. We got three main log properties. We've already seen that there's some in the previous section. If you have log of something plus log of something, addition becomes multiplication. If you have log of something minus log of something, well, subtraction becomes division. If you have a number in front of your log, and that's typically a number, it doesn't have to be, it can be a variable, but if you have a number in front of your log, you can put that as your power. So addition becomes multiplication, subtraction becomes division, and then my power, or a number out in front becomes my power, and vice versa. You can go either direction. Well, let me show an example. Let me clear this off. Seems like it's getting slower. Not a good sign. Okay, so we're going to have log base 3 of 9x squared over y to the third. Now here we're starting with a single log, and we want to expand this into separate logs. And we'd like to get the variable by itself with a log in front of it if we can, and then to simplifying numbers. Now you always have to ask yourself the main thing that's happening here. We got 9 times x squared, we got multiplication, we got second power, we got third power, and we got division. When I say the main thing, I'm talking about what's using every item in your problem except for the log. And that'd be division. All of the top divided by all of the bottom. That would use all these different items here. Well, division, from property 2, we can rewrite as subtraction. So this becomes log base 3 of 9x squared minus log base 3 of y to the third. Now looking at our first log, we have to ask ourselves the main thing that's happening. We got 9 times x squared, or we got the second power. And what would use everything is multiplication. The second power would not use everything because the second power only applies to the x. So multiplication is the main thing that's happening. And so from property 1, multiplication becomes addition. So this is going to be log base 3 of 9 plus log base 3 of x squared. And this carries down. Minus log base 3 of y to the third. Now we saw this in the previous section, or 2 sections ago. If you got a number here, you try to rewrite it as this base to a power. It doesn't always work. But in this one, we got 9 as 3 squared. Now there's only one thing left to do on these last 2 logs. They both have powers. Remember I said we'd like to get a single variable with a log in front of it. So here I'll take this 2 and put it out in front. So we got, this is from property 1. So we got 2 log base 3 of x minus, I'll take this 3 and put it out in front. So minus 3 log base 3 of y. Now notice here the 3's match, so the log and the 3 is going to cancel. And we're left with the exponent, which drops out of the exponent. So we've got 2 plus 2 log base 3 of x minus 3 log base 3 of y. And that would be our answer. Again, we got the x and y by themselves with a log in front of them. And then we simplified any numbers. Now that's going one direction. So let me go ahead and clear that off. That direction is useful if you're in calculus. By expanding it in that manner, then we can easily solve other problems, such as derivatives. Second type we're going to look at, as soon as this finishes, is where we're going to start out with multiple logs. So we got, try it again, 5 log x plus 3 log y minus 4 log z. So we're going to start with multiple logs. We want to merge it into a single log. Pretty much you follow your order of operations, with the exception you cannot use properties 1 and 2 if there's any numbers in front of your logs. You can only use these if there's no numbers in front of the logs, which works out well because our third property says if you got a number in front of your log, you can put it as your power. Now I notice on this one, all of them have numbers in front of the logs. So first thing I'm going to do is put that number as a power. So I'm going to have log x to the fifth plus log y to the third minus log z to the fourth. Now order of operations says we handle it from left to right, or addition or subtraction. Now here we got log of something plus log of something. And that's property 1. Log of something plus log of something, addition becomes multiplication. So that becomes log x to the fifth, y to the third. And this carries down. If I can get it to right. There we go. Now we have log of something minus log of something. Well, that's the second property. Log of something minus log of something, subtraction becomes division. So this is going to become log x to the fifth, y to the third, over z to the fourth. And that's our answer. So we work to get in a single log. Now let me clear that off. Grab a drink while it's doing that. Okay. Now that was really those first three items there, and we saw the change of base already. Now in section 4.5, exponential and log functions. I should actually say exponential and log equations, but first thing we'll do is take a look at solving exponential equations. And we have something called the equality of exponents. And it says if you have b to the p is equal to b to the q, then you can set p equal to q. Well, I'll get there eventually. There we go. Now the b's are typically numbers. So you got a number to a power equals number to a power, then you can drop the numbers and set the powers equal to each other, the exponents. Very simple idea. Not so simple to always get in that form though. That's the challenging part. Let's say we got 2 to the x is equal to 8. Now using the equality of exponents, what we do is we start with the larger number and we try to rewrite it as the other number to a power. Now 8 is 2 to the third. Now the equality of exponents says if you rewrite both of these as the same number to a power, then you can cross those numbers out. So cross the 2's out and you set the exponents equal to each other. So we get x is equal to 3. Again, simple idea, right? But if you have 8 to the x is equal to 16. They're not all so easy where you can look at them and see. If I try to start my larger number, the 16, there's no way I can rewrite it as 8 to a power. 8 to the first is 8, 8 squared 64. So instead I have to look at both sides. And I can rewrite both sides as 2 to a power. So 8 would be 2 to the third, and 16 would be 2 to the fourth. Now notice that the 8 to the x already had an exponent up there, so when I put the new one up there, it's multiplied by what's already there. Now equality of exponents says, since they're both 2 to a power, I can cross the 2's out, and I set the exponents equal to each other. So I got 3x is equal to 4. And then solve this, divide both sides by 3, and we end up with x is equal to 4/3. And that would be our answer. Now let me clear off this page. And that's equality of exponents. Now if I have 3 to the x is equal to 8. Try to use the equality of exponents. I start with a larger number, which is 8. There's no way I can rewrite it as 3 to a power. I focus on both sides. There's no way I can rewrite both sides of the same number to a power. Well, it fails, doesn't it? We got another technique for solving exponential equations. And let me put that here. Solving exponential equations. Our first step is to get the part with the variable in the exponent by itself on one side. Step 2 is to take ln to both sides, natural log. Step 3, use properties of logs to get the variable out of the exponent. Step 4 is solve for x. Okay. Step 1. Get the part of the variable and the exponent by itself. Here's a part of the variable and the exponent. It's by itself. There's nothing in front of it. There's nothing after it. We just got 3 to a power. So that's done. Step 2, take ln of both sides. So take natural log of 3 to the x is equal to natural log of 8. Step 3, use properties of logs, get the variable out of the exponent. Remember, if you have a log of something to a power, you can take the power and put it out in front of the log. So we're going to have x natural log of 3 is equal to natural log of 8. And our last step is to solve for x. Well, natural log of 3 is just a number. If I plug that in my calculator, I get some kind of decimal. If you have a number next to a variable, remember how you get the variable by itself is you divide both sides by that number. So that's what we'll do here. We'll divide both sides by natural log of 3. Now when we do that, these natural log of 3 is going to cancel over here. And we got x is equal to natural log of 8 over natural log of 3. Now that would be our answer, the exact form. If you want a decimal approximation, then you would plug that into your calculator. Let me show another one of those. One a little bit harder. Feeling pretty lucky. Maybe I am. It's going slow there. Well, there we go. Watch it crash here any minute. Let's say I got this. Now our first step is get the part of the variable and the exponent by itself one side. Well, it is by itself. There's nothing in front of it. There's nothing after it. We just got 5 to a power. Step 2, take natural log of both sides. Step 3, use properties of logs, get the variable out of the exponent. Remember, if you have a exponent here, you can put it out in front of your log. Now, since there's 2 terms, I have to keep parentheses around the x minus 1. Now we want to solve for x. And our first step is to get rid of parentheses. Now natural log of 5 is next to the parentheses, so it indicates multiplication. And natural log of 5 is just a number. So we're going to take this number here, and we're going to multiply it times x, and we'll multiply it times negative 1. It's real easy to multiply those together. You just put them next to each other. So we're going to have x natural log of 5 minus 1 natural log of 5 is equal to natural log of 2. Now we're trying to solve for x, so I'm going to take this negative natural log of 5 over to the right side. So we have x natural log of 5 is equal to natural log of 2 plus natural log of 5. And then our last step is to divide both sides by a number behind our x in this case. So we'll divide both sides by natural log of 5. Now when we do that, those natural log of 5 is going to cancel. And we got x is equal to natural log of 2 plus natural log of 5 over natural log of 5. Those natural log of 5s cannot cancel, in case you're wondering. It's because of the plus in there that messes it up. So that would be our answer, or you could plug it in your calculator to get the decimal approximation. Now let me clear that off. And let's take a look at the log equations. Okay, so log equations. Step 1. Get everything with a log on one side and numbers on the other side equals. Step 2. Use properties of logs or basic algebra to get a single log. When all is said and done, you want to say log of something on that side. No numbers in front of it, nothing after, it's log of something. Step 3. Use the definition of log to rewrite in exponent form. This is the b to the p is equal to q definition. Step 4, solve for x. And step 5, check your answers. Specifically, we just want to check to make sure we don't got log of 0 or log of negative number. We don't have to fully check it, unless you just want to. Let's take a look at a problem. Log base 3 of x minus 1 equals 2. Step 1. Get everything with the log on one side, numbers on the other side. Everything with the logs over here, numbers over here. That's done. Step 2. Use properties of logs to get a single log. Remember what I said we're looking for. We're looking for it to say just log of something. Well, that's done. Now step 3. Use definition of log to rewrite in exponent form. The b to the p is equal q. Well, remember your base is your b, then whatever follows that is your q, and the other side of the equals is your p. And our exponential form is b to the p is equal to q. B we said was 3, p is 2, and q is x minus 1. And then step 4, solve for x. 3 squared is 9. Take negative 1 over, becomes a positive 1. And we get x is equal to 10, maybe. We have to check it. We have to make sure it doesn't cause log of 0 or log of negative number. Well, if I put 10 up here, 10 minus 1 is 9. That's not 0, it's not negative. So that's our answer. Now you can't forget your special bases on these. For example, if I have natural log of x plus 5 is equal to 2, first step is to get everything with the log on one side, numbers on the other side. That's done. Step 2 is use properties logs or basic algebra to get a single log. We have a single log. That's done. Step 3, use definition log to rewrite in exponent form. So you're going to take whatever your base is. We don't have a number here. But remember, if you have ln, your base is e. And then this will be your q, and this will be your p. So our exponential form is b to the p is equal to q. So we plug in everything. B we said was e, p was 2, and q is x plus 5. Now we want to solve for x, so I take the 5 over, and we got e squared minus 5 is equal to x. And if I plug that back in up here, the 5's would cancel, and I have e squared, which is not negative, and it's not 0. So that's our answer. Now there's one last shortcut I want to mention, and then I'll stop the video and answer any questions you might have. I won't actually finish this problem, I just kind of started. You'll see why. Okay, let's say I have this problem. Log of x minus 1 minus log of x plus 3 is equal to log there it goes, log of 5. If everything has a log on it, there's a shortcut that says you're going to use properties of logs to get a single log on both sides. Well, over on the left side, we have log of something minus log of something. Subtraction becomes division. So this becomes log of x minus 1 over x plus 3 is equal to log of 5. Now, if you can get a single log on both sides, log of something equals log of something, then you can drop the LOG parts. So then we got x minus 1 over x plus 3 is equal to 5. And then we'd solve it. You still have to check to make sure it doesn't cause log of 0 log of a negative number, but that's a shortcut. Now I'm not going to solve any of these last ones here. They're basically combining what we've already seen with perhaps a compound interest with techniques we just looked at for solving different types of equations. And there's other ones you could use besides that. There's a half-life formula, exponential growth and decay, and so forth. So let me go ahead and stop the video.